In this question, we have to collect some definitions and discuss some stochastic process. The first one is the WSS process. A stochastic process is called WSS process if its mean is a constant, and also the autocorrelation function is only a function of time difference. That is, RT1 T2 is a function of T1 minus T2, which we use TOR to indicate this. The discussion of WSS process is that WS process you only use mean and autocorrelation functions. Because of this, we can easily get the second order density by the mean and autocorrelation. Moreover, in the system design, we already know that if the input signal xt is a WSS process, and then it goes through a LTI system ht, then output signal yt is also a WSS process. Second one is the independent increment process. Independent increment process means that if xt1 minus xt2 and xt3 minus xt4, they have no overlapping intervals, then these two are independent. The discussion of the independent increment process is that so far we have already known some independent increment process such as Poisson process, random walk, Wiener process. Then the third one is the Markov process. Markov process simply means that past have no influence on future when we are given the present. The discussion of Markov process is that by now we have quietly known a lot of processes that is defined as Markov processes such as Poisson process, Poisson impulses, semi-random process, semi-random telegraph process, random telegraph, random walk, and Wiener process. They are all Markov processes. Then the fourth one is the normal process, which is also known as Gaussian process. A process xt is defined as normal or Gaussian if the random variable xt1, xt2 to xtn are jointly normal for any n, any t1 to tn. And the probability density function of fx x1 to xn, t1 to tn equals to 1 divided by square root of 2 pi to the power of n times square root of delta c times e to the power of minus half times x minus eta transpose times c inverse times x minus eta. In this case, x is in a vector form, and eta is the expectation of x. Then c is the autocorrelation function defined as e x minus eta times x minus eta transpose. The discussion of the Gaussian or normal processes is that the normal processes can be completely determined by its mean eta and autocorrelation function c. Then the fifth one is the SSS process, which is also known as strict sense stationary process. A process is said to be SSS process if the statistic is not affected by a shift on the time axis. We can simply use the probability density function to indicate this property, that is, fx x1 to xn, t1 to tn always equals to fx x1 to xn, t1 plus epsilon to tn plus epsilon for any given epsilon. Then we have to do some discussion. One interesting thing is that if we have a WSS process xt, and we also know that xt is also a Gaussian process, then we can determine that xt is SSS process. Then the sixth one is the white noise. White noise is a process such that its values at different time xi and xg are nearly independent. And actually they are uncorrelated, since that the autocorrelation function of Rxx T1 T2 equals to Q T1 times delta T1 minus T2. So if T1, or in this case we use Ti Tg, if I is not equals to G, J, the autocorrelation function always equals to 0. So we can know that if they are not the same process xti and xtg, they are always uncorrelated. That is the property of the white noise. Then the seventh one is the mean ergodic process. The mean ergodic process is defined as limit t equals to infinity 1 divided by 2t, the integral from minus t to t xt dt equals to the expectation of xt. The eighth one is a process named martingale. The martingale process is defined as if the expected value of xt given xx equals to x1 simply equals to x1. Then we have to do some discussion. The martingale process simply means the conditional mean equals the condition. And that's quite interesting that the martingale means the strength we put on the horse to constrain something. And we think that is quite reasonable because in this case, the conditional mean equals the condition. So we can see that